So welcome everyone to Chip Agent session. So today we're going to talk about beyond automation, how Agentic AI is reinventing chip design and verification. So my name is William Wang. I am founder and CEO of Chip Agent. I did my PhD at CMU. So my background is in AI. I did my PhD at Carnegie Mellon University, being a full professor at UC Santa Barbara for many years. Pretty much work with all of the companies you can name in this area. Super excited about building the next generation of AI agent for design verification, because I've actually started building the first reinforcement learning agent called Deep Pass back into 2017. And now it's really a wonderful time, right, to really see the breakthrough in this area. And we also work closely with John Bowers. He's a serious entrepreneur and also a pioneer in silicon photonics. So Chip Agent is downstairs. Our team has about 10, 15 people right now. So you're welcome to come downstairs to talk to our engineers after the talk as well. A little bit about the company, right? So we are a relatively young company. We have very extensive experience in design verification, agentic AI solutions. We started last year, about a year ago, right? So that's why you're seeing us the first time, because last year we just started. And we're a Series A company, and we are based in Santa Barbara, California. We're opening an office also very soon in San Jose, Santa Clara area. So looking forward to work closely with all of our colleagues and customers. We really believe AI agents is for everyone, right? We want to empower you. We want to empower all of the engineers, the scientists, for you to do a better job. And we really believe in the future, we have a grand vision that AI agents will power the next generation of chips. Whether you're doing memory chips, whether you're doing AI accelerator, AI agent will really fundamentally change how you're doing design and verification today. Chip Agent has proven success. Right now it's deployed in production at top 10 companies in the world. And we've seen companies that actually produce 15 billion chips actually caught bugs using chip agents in production. And we are very excited about the result as well. So we also have the saved out result I'll tell you in just a second. So what exactly do we do? Well, we support a very wide range of design and verification flows. Starting from the design, we can take your data sheet and start it to help you understand whether your definitions in your data sheet and also in your spec are consistent or not, right? And then when you're integrating different IPs in your SoC, now you can actually start, doing cross-checks and make sure that things are correct. We'll also help you to generate RTL code. We'll give you the result in just a second. We're very proud of our self-taught result in this area. And you, of course, do RTL documentation. We can help you to translate your complex finite state machine into a readable transition table. Verification, we support the full flow, right, in terms of generating test plan, full verification, generating system verilog assertion, help you to generate a UVM test bench from scratch, and also do debugging as well. Some of you have been to our waveform debugging session. So we're pretty proud about our result. So this is the overview of today's TED Talk. I will do a very brief introduction about the technology. Then I'll hand over to Ke-Shun, who is our head of research. He'll tell us more about AI agents, right, in general, what it is and why is it the best, right, for design verification. And then I'll hand it over to our head of engineering, Mihir Aurora. He will help us to walk through a live demo of chip agents in action. All right, so what are the challenges in design verification? I don't have to tell you too much about it, but I think everybody is struggling because the chips are growing from millions of gates to tens of billions of gates to trillions of gates, and that's extremely difficult, right? Because the test bench is getting even more and more complicated. So people are having a very hard time in the industry meeting deadlines, right? We see project delays went up from 60% to 75% last year. And the issue is that sometimes there's also communication between the design and verification team, and those cycles will actually stretch really, really long. And traditional methods are great, but it's just that they were really designed from 30 years ago, right? So there's a lot of limitation when you're trying to scale, right, to billions of logic gates. And finally, I do want to mention that because of the complexity in the front-end design, while the back-end also got really complicated, and we did see a drop from 20% first-time silicon success rate to about 10% across many companies, across different projects. So that's why we're here to help. And specifically at Chip Agents, we build specialized AI agents for design verification. We've benchmarked internally, we work with our customer closely. We found it's about 80% reduction in your development time. And specifically, we also found that many customers started using Chip Agents to actually trying to improve the accuracy and precision, because now human, right, is not very good at reading like 2,000 pages of PCIe spec, but actually AI agents is pretty good at doing that. So that really help us improve, right, the accuracy in design, in verification, and that's extremely useful. Other things I want to mention is that AI agents get better over time, right? So AI agent can learn from the feedback from yourself, from AI, from all these different feedback tools, anything you have to actually help keep improving, right? That's really exciting because traditional tools, right, they don't improve over time, they stay the same. Other things I want to mention is that we do have the state-of-the-art result and agentic AI performance on NVIDIA's Verilog Eval benchmark. So we benchmark very closely using all these different foundation models. We look at AI agent solutions as well, but we have the best result on NVIDIA's Verilog Eval benchmark. So NVIDIA provide basically the test bench, right? These are the Oracle test cases. And this benchmark is a design benchmark. So you go from specification to the RTL design. Anyone can generate AI code. And then you send the AI code into NVIDIA's test bench, and it will tell you, right, what is the percentage of cases, right, that actually pass. We got the best result in January, and it's about 97 to 99 on 2 of the subsets. We also have the best result in high-level synthesis in Python programming. So if you're interested in Python, there's a benchmark by OpenAI. It's called Sweetbench, right? And Sweetbench is the go-to benchmark that all of the big tech CEO they look at every morning. And we had the best result from last year, from 2024, using our original research. It's called Sweet Search, where we integrate Monte Carlo tree search, right, with iterative refinement. And this was done by my PhD student Antonis, also our co-founder Kashing. This was presented last month in Singapore at the International Conference on Learning Representation, the premium conference on machine learning. Okay, so what do the actual customers say? This is very important because we have the best benchmark result, but what do the actual customers say in production? So this is the reality is that Chip Agent is in production with top 10 semiconductor companies. They've actually caught bugs, right? So people were sending us messages and they're telling us, I used Chip Agent to generate invariant assertions that actually found bugs, right, in their projects that saved them millions of dollars. So that's super, super exciting for us because this is where we see the future, that AI agent is helping you to do the task better, right? To actually help you to run more tasks, right? Who doesn't want to run more tasks, right? If you always have more tasks to run, you'll be always very happy as a verification engineer. So we talk with many leaders in the space as well. So Raul Capasano, the longtime CTO at Synopsys, he evaluated our technology and he said, we went from drawing schematics to RTL, and now 30 years later, finally, we're onto something. And he found Chip Agent very exciting because now you have more time, right, to think about your microarchitecture designs, and you don't have to write all of the tedious directed tests or constrained random tests yourself. So that saves you a lot of time so that you can spend more time working on productive solutions. Other things I do want to mention, I think last year was the year of AI systems for design. This year at DVCon, we also unveiled our first debugging agent and function verification agent. We really believe into future years, the future is going to be fully agentic AI solutions, right? We have the grand vision that imagine an AI agent actually help you, right, with the entire tape-out process. I think that will come in the next few years, and that actually help you, right, to free your time so that you have more time, right, to think about creative, microarchitecture designs and also the, verification plans. Okay, so next on the stage, I'd like to welcome Ke-Xun, who is our head of research, to tell you more about AI agents. So Ke-Xun, please.
Thank you. Thank you, William. So I want to talk to you about what are AI agents and why do we want them, specifically why do we want them in chip design and verification. So AI agents are based on large language models. And so before we talk about agents, we need to talk about language models. So what are large language models? Essentially, they're next word predictors. For example, let's look at the first sentence. DAC 2025 is in mask. So the model is trained to predict what the word is for mask. And here are some probable next words. San Francisco, it's the correct answer. California, likely. America, also correct. But there are also some next words that you probably wouldn't see following DAC 2025 is in. For example, hashtag include or supercalifragilisticexpialidocious. These are unlikely words that will follow this sentence. And next word prediction can happen in many different contexts. For example, it can also happen in Verilog code. If you have this Verilog code and you give this string to the model and asks it to predict what's in the mask, a model that's trained on a lot of Verilog code should be able to tell you that you should put in reset. And it can also be trained to answer questions, because question answering, if you think about it, can also be formulated as a next word prediction problem. For example, question what's 5 plus 7, answer, and if the model is trained on a lot of math data, it should be able to fill in the mask 12. Okay, so they're pretty good. You can chat with them, you can ask them to write some emails for you, but there are many things that they actually cannot do. So what they can do is they can understand a single short system Verilog file. They can fix bugs in a single file. They can generate test benches for a small single module. They can read and check a 5-page PDF. But that's not what you need. You're actually dealing with much more complicated problems. And language models alone cannot do a lot of the things. They can't understand your entire design. They cannot find and fix bugs in a 5,000 file code base. They cannot execute test plans for an entire design. They cannot improve coverage. They cannot run simulations. And they cannot cross-check a 5,000-page PDF spec with your design. So there are so many things that they can do. And the reason why they can't do it is because they are basically word generators. They can't take actions. But now, with agents, they can, because agents are large language models that can take actions. So while language models make mistakes and that propagate with each prediction, agents can actually do self-correction by interacting with the environment, by using the tools that humans would use, by reading the documents that humans would read, and they can actually be more autonomous, interact with the environment, and intelligently decide what context it needs to solve a problem, just like how human engineers would. And language model agents have been a huge success. So here's an example. In software engineering, this is a benchmark called testbench, where the language model agent is tasked with fixing a software engineering issue. It's a pretty big issue. It's a pretty real-world code base, sklearn. And the model needs to take a look at the description of the issue, take a look at the huge code base, and actually modify some of the files in the code base in order to fix bugs and then pass tests. So very realistic. And language model only approach with GPT-4, the best language model back then, had a resolve rate of 2.8%, which is really not something you would want to use in your daily life. But with agents, they got 8 times better. A naive language model agent baseline can get you 23% resolve rate. And with our technology, with the technology that we developed called SweSearch, we got the best results in 2024, which is 62%. Much better. And you would actually want to use something if it's as high as 60%. And it's a huge success in software engineering. Over 25% of Google's code is now written by AI. And a lot of programmers have tried AI, and Wired, in their survey, said that 17% of programmers use AI for their software engineering tasks at all times. So how about chip design? Well, one interesting thing about chip design and verification is that the existing benchmarks aren't really benchmarking agent workflows. They have very simplistic problems that has an input spec of smaller than 100 lines, and the output is a single file that's also less than 100 lines, and they're toy problems. And we are building internally a new benchmark called Chip Agents Bench, where we actually give our agents real-world tasks on real designs that have been taped out. It has thousands of files, hundreds of thousands of lines of code, and huge waveforms and log files. And we want the agent to be able to deal with these real-world problems. And in the future, we plan to open source this benchmark to the community so that people can actually see what kind of tasks can agent do and what tasks do they do well. So here's an example from Chip Agents Bench. The agent has access to a huge design, its test benches, some simulation results, and there is a bug in the design that fails tests. And we ask the agent, why is this test case failing? And we ask it to look at the waveform and find out. And the evaluation criterion we use for the agent is to check if its changes to the design can pass the tests. And here's some results on a subset of Chip Agents Bench, where we compare the performance of a state-of-the-art language model with our Chip Agents designed waveform agent. And as you can see, as the reasoning budget gets higher, our agent can solve more than 50% of the bugs by looking at waveforms, looking at the design, looking at the test bench, and by interacting with the simulation environment. But the state-of-the-art language model, even with a very high reasoning budget, can only do 30%. So yeah, that's what we're doing for chip agents. And we believe that AI agents can do much better in chip design and verification than mere language models. OK, now let's welcome to the stage Mihir Arora, our head of engineering, to tell you how AI can actually accelerate verification in production.
Thank you. My name is Mihir Arora. I'm head of engineering at Chip Agents. OK, so we actually want to talk about, like what William was talking about earlier, the Chip Agents is actually deployed in production. Kashin is also talking about the work that we've done internally on research and so forth and more benchmarks. But we actually want to see what we can do today, right now. And so that's actually what we're going to show you. So I don't want to present more slides to you guys. I actually want to show you real designs. I want to show you guys real systems. And I want to do real things that design and verification engineers care a lot about. So I've pulled up Visual Studio Code here, and I've actually pulled up the Chip Agent interface for people to take a look at and to understand exactly what we want to do. We're going to focus on a big part of the DV flow. Earlier, William showed you that big slide where we had lots of different flows that we do support. We support the full flow for design, for verification. Architects use our solutions. Formal property verification engineers use our solutions. But I'll start off with some work on design verification. The way that we're going to do this actually is that I like to showcase really going from specifications, sizable specifications that are used in the real world, all the way through to verification collateral that DV engineers can actually use in order to kickstart the process of design verification. So this is the ARM AXI protocol spec that we have. It's a 300-page document. I just downloaded it from ARM's website. Most people are familiar with an AXI. That's why we choose this particular use case. And I'm actually going to ask chip agents directly to read this spec, and I want it to produce for me an exhaustive test plan. I actually want it to go through and examine all the different sections. There's something like 13 different sections. And in a couple of minutes, I want to go through and produce a very hierarchical specification for how exactly I'm going to do my testing. I want all of my test items to be enumerated for me. I want it to be nice and traceable with references. I want it to generate it section by section. I want it to have step-by-step information on how to provide stimulation, how to provide the verification criteria. I want to do all of this work, and I'm going to pass off all of this to chip agents to do in a very autonomous fashion. What you'll notice about the particular interface is that I'm really providing only a little bit of information up at the top. The information is up here. Hopefully, if everybody can read that, I'm really just asking it to read the actual AXI spec, and then I'm asking it to write the test plan. There's a couple of requirements I handed off to it, but on the whole, it's quite a small affair. This is sort of the style of ticket that you might pass off to another engineer on your team. You might put it up on Jira or a similar sort of ticketing system. And then you'd probably wait around 3-ish weeks, maybe 4 weeks, it depends on who's doing it, maybe some junior engineer on your team to go parse through this document, a 300-page document, and put together an actual test plan for you. But Chip Agents is actually going to do all of this work for me in about 5 minutes. So how does it actually go about doing that process? Well, Chip Agents is an AI agent. We've been talking a lot about agents, and now you get to see one. The difference between standard systems like LLMs and agents are that they're embedded in your environment. They can take actions against your environment, and when I boot up Chip Agents inside of a directory, it has access to different files within that directory, and it can take actions against them. With my permission, it'll be able to edit files. It can run huge sections of my EDA flow, go out and run scripts that it produces itself or scripts that already exist. It'll figure out how to build and link your project. You can boot this up on a Linux server that you have, for example, to run batch jobs for your entire EDA flow, for example, simulation and so forth. And Chip Agents will figure out how to do all of that work on its own. To give you the example here when we're working with the AXI protocol spec, the first thing that it actually did is, of course, figure out where the spec is. Nowhere in my actual input did I tell it where the AXI spec is in my environment. It figures that out on its own. We expect our tools nowadays to be smart and capable enough that we can actually delegate to them, right? And this is the reality that we are working towards and have made possible today. After it's actually found the specification, it's trying to find high-level information about it. Maybe things like the table of contents, chapter structures, section overviews, and so forth. And then it's starting to put together the actual test plan. This file it's producing for me piece by piece here, should go all the way down. It starts with this little introduction section, a nice preamble and some organization for me. You can see it's got roughly 16 sections which it's going to plan to produce for me. And then it's going to go through the document piece by piece and understand exactly how we want to codify the quasi-formal statements that are made in English in the AXI spec into something that we can actually do a little bit more exhaustive verification of. So it's going to look at chapters A3, it's going to look at clocks and resets and handshakes, and it's going to add those components to the test plan. Then it's going to go through and look at channel dependencies, handshake signals, etc. And it's actually going to start producing more test items. And it's going to continue in this fashion. It's going to be very methodical. It's going to go through and it's going to look at a section, write about that section, codify it into a set of test items that I can actually use, and then continue. Of course, what will be more interesting to do from this? This is already interesting and useful. However, we can then go from this test plan to actual UVM collateral, which is the interesting thing that, especially on the design verification side, everybody is very interested in doing. Let's look a little bit at the actual test plan. There's a lot of stuff about clocks and resets and so forth. Let's maybe look at something that's a bit more interesting, like the channel handshakes, and then we'll go through and look at more interesting stuff therein. We can see that's very hierarchical in style. This is all in Markdown at my request. I'm a Markdown person. I like plain text. We can look at things like the channel handshake mechanisms here. This is specifically in reference to section A 3.2, page 38. If anybody has an AXI spec on hand, they can in fact go to page 38, and there's the channel handshake section. So none of that is made up. It's real. And this document is being produced for you right now, right before your eyes. And you can look at particular test items, like the valid before ready handshakes, the ready before valids, the simultaneous valid readies, the valid persistence, and so forth. There's references for each of these pieces. It tells me how to do stimulation, how to do the actual stimulus, how to do the actual verification, and it's being very, very exhaustive and thorough. While I've been talking plenty, Chip Agents is actually done. I can keep scrolling through here, and there's multiple hundreds of lines of Markdown that's been produced. I can go and look at the different transaction types, the transaction responses. There's millions and millions of different transaction responses. I mean, it's a on-chip communication protocol. There's a lot of different response types. OK, EX, OK, error response types, different special response types. There's a reference for each of these sections, right? And we can keep going. Together, there's actually a good number, quite a large number of different test items that have been put together. And from here, we can actually really start a serious verification effort of the AXI protocol. I think that's great, but you know what's even more interesting? Is that I can actually boot up a new entire instance of Chip Agents, and we can work on top of this test plan, and then actually produce some UVM collateral as well. So that's actually what I'm going to do. I'm going to ask Chip Agents right now. I'll say that let's use the AXI protocol and test plan to write a UVM test bench for the AXI protocol. I'll give it a couple of requirements here. Like, for example, I'll ask it to, let's say, start with the interface and the transactions. I'll tell it to write all the sequences next. and put them in separate files just for organizational clarity. I'll say to write sequences in a very randomized style. We could do directed tests instead, but we'll start with something very randomized, and then we'll say then write coverage, split up into different files based on subfeature. And that's all I really have to say to chip agents. I'm going to toggle on the autonomous mode here, and then this is a completely hands-free operation. Chip agents, this process, it takes a little bit longer because there's multiple thousands of lines of system Verilog to write here, system Verilog and UVM. But it takes about 8 to 10 minutes, and it actually bootstraps an enormous part of our verification effort. A common question that we get when talking about chip agents is, well, okay, so you can generate a lot of material from scratch, but I actually have an existing huge amount, potentially decades of verification work that I need to leverage. How do I leverage all of those maybe 20 years of test benches and designs? Well, chip agents is actually thoroughly optimized for the situation where you already have existing test bench infrastructure. If you have that existing infrastructure, you can plop chip agents directly inside of your repositories, ask chip agents to understand how to build and simulate and run linting and so forth, and then it can immediately start writing new sequences for you, writing new coverage for you, extending your behavioral model with new features. It can do all of this work and thereby save you a huge amount of time. What is, I think, much more interesting about our flow compared to a lot of existing technology is that we bet really strongly on autonomy. This technology, it's improving at an extraordinarily rapid pace. As Kashin was just talking about, we're starting to see systems that can actually debug serious problems, do serious root cause analysis. We had such a session on Monday as well. One floor down from us, we had one of our machine learning engineers talking about root cause analysis directly from waveforms and operating over design under tests and so forth. The progress there shows that really there needs to be a strong belief in the autonomy of these systems going forward, and that's how we have made our bets, and these have paid off. Here, we're showcasing a very flexible flow on the whole. Earlier I was working with the specification, but now I'm actually working with all of the DV collateral. Likewise, we can work with the design collateral and actually produce new modules, integrate modules into existing systems at a large scale, run simulation, run linting, use that as feedback, get things compiling and working. Lots of design engineers are writing smoke tests for their modules using chip agents and so forth. Let's actually look at some of the material that's been generated by chip agents. I'll pull it over to this side, maybe organize my windows a little bit. So here's all the AXI interface for us. So this is all just boilerplate. I'll say we'll get to the sequences, and that'll be more interesting and more fun for all the DV engineers to take a look at. But it's great that it actually put together the AXI interface. I mean, if this was all the chip agents did, it would still save me time. But it does a lot more than that. Everything is nicely parameterized. We've got all of the different channels. There's a huge number of them. A common question is, where does chip agents get all of this information? But you guys actually all saw. There's a test plan that it produced for me, and we provided that to chip agents, and there's a specification which chip agents use, and that's how it determines where it gets all of these different wires and channels from. And so it sets up this entire interface actually for me here. It's got different clocking blocks here for all of the different components on the actual bus, the actual mod ports, and a number of simple assertions here that we can actually use to assert things like valid stability and so forth. So it's great that it has all of this material here, and all of that was set up. In the meantime, it's working away at transaction items, and then it'll put together different sequences therein. So there's additional material that I think today we don't have as much time to showcase. However, one of the really interesting things that we can do is log analysis. There's a huge amount of effort. While we're all very interested, and here let me bring up the actual transaction class so some people can take a look as I'm talking. There's a huge amount of effort on both the design and the verification side that is constantly dealing with and wrangling with your simulators and their logs and their output. It's quite a party trick. You can actually introduce chip agents into a new, unfamiliar design, ask it just how to build. How do I build this process? How do I run simulation? Chip agents will figure out your entire build process. And these can get very, very involved, of course, in commercial settings. And it can do that work for you. There are many customers of ours who are actually looking to port a particular design or test bench from one type of simulator to another. So there can be a little bit of differential, right, between one simulator of choice and another simulator of choice. Not everything is totally simulator agnostic. So chip agents can actually be set up or discover how to compile your whole design and test bench infrastructure, and then work on porting it to another different simulator environment. And it'll look at all the different simulation logs, the compilation logs, and then work slowly to port that one by one. What is otherwise an extremely manual and tedious process, chip agents is able to automate this work. We can look briefly at the transactions. It's a nice standard set of transactions that's all been nicely commented for us. It has all of the different transaction types, the burst types, the response types, size encodings, and so forth. The actual transaction here has been produced. It's following all the nice UVM syntax and style for me, extending the different sequence items and so forth. We've got different constraints here. My favorite, the transactions must not cross the 4 kilobyte boundary. There's really a lot of attention to detail here that Chip Agents is utilizing this process. Okay, and then a million different other constraints and all of the UVM boilerplate in order to set things up and make them work, right? In the meantime, Chip Agents has been hard at work producing different write sequences for me. It actually put together a base sequence as well. Let's see, yeah, I can control click on that. So we've actually got a base sequence here that it produced as I was talking, where it has a bunch of standard constraints that's produced here. As I said, I did request a nice, highly randomized test bench with nice, highly randomized sequences, so it is fulfilling that promise. It's got plenty of functions here that we can utilize in order to do things like send different transactions. It's extended those base sequences to produce all of these write sequences, write-specific sequences with all of our different constraints on lengths, sizes, bursts, number of transactions, and so forth. Here we've got the distributions for the different cache attributes, the different protection attributes, QoS distributions, and so forth. So we've got all of this material. Together, we've actually got a huge number of different sequences. If I pull up my actual file viewer here, we've got the different read sequences, and there's a good couple of hundred lines of code there, another 100 here for the write sequences, another couple hundred for the different burst sequences that are involved as well. And this is including the interface and the transaction class that were set up for us. We can look at the different burst sequences here as well. What's really interesting is that you can actually have here, let me scroll all the way down so people can look at Chip Agents and what it's doing. What you can actually have here is traceability all the way from your specification to the test plan. For all of those test bench items, it can actually annotate your test bench with the particular test item of interest. And that gives you some level of traceability, right? We want hierarchical systems so that we know that we've actually fleshed out the verification effort completely. And here Chip Agents is enabling that in a much more automatic way. What is otherwise pretty manual and tedious effort for humans, Chip Agents is able to actually offload a huge amount of this effort, right, onto the agentic process. So it's still working away on different sequences. Now we've got actually outstanding sequences for different outstanding transactions and randomized timing and so forth. So we've got the actual transaction generators here, back pressure, outstanding transactions, the unique IDs, and ordering constraints and so forth. It's pretty involved, And of course, one other question that we often get is, what about the customizability? Well, Chip Agents is really flexible. Again, our bets are on two different things, autonomy and customizability. You can customize Chip Agents to utilize your own internal UVM libraries. Every single large corporation, they all have their own internal UVM set of assertions or just more broadly the whole verification methodology. And we have specific systems that are set up, specific sorts of customization that you can perform in order to get Chip Agents to use all of that material. It'll use your company style guide so it produces nice homogeneous code. And there's tons of tricks and ways that we allow you to administrate Chip Agents at an organization scale to ensure it produces nice homogeneous code for all of your engineers. Additionally, like I was saying earlier about traceability, if you actually look at any of these individual sequences, you can trace it nicely back to the actual test plan, right? This was all predicated actually on executing the test plan. Chip Agents has been very successful. We've introduced Chip Agents into organizations, for example, on the DV side and other areas as well. But if I talk about the DV side for the moment, oftentimes you're about, let's say, 40, 50% of the way through your test plan. You've got a million more sequences to write. You've got a ton more coverage to write. You can immediately drop Chip Agents into your organization and get very productive very quickly, get a lot of immediate value out of having Chip Agents produce all of these sequences for you, because you always have more to write. And as you can see, Chip Agents will autonomously discover all of the configuration within your project, the file hierarchy. It'll read your documentation and figure out where everything needs to go. And it can therefore take the test items of interest, read the existing sequences, reuse existing infrastructure, produce new sequences, and place them in the correct spot so that you can actually continue to utilize and extend the existing work that you have. So you get immediate value out of bringing Chip Agents into an organization. And we've had a lot of success through doing that. Let's look at some actual coverage as well. I'd say the two key things that we really like to emphasize is Chip Agents is fantastic at writing sequences. Of course, the entire rest of the UVM infrastructure, but fantastic at writing sequences, and it's fantastic at writing coverage. Here's all of our transaction type coverage, our address coverage, our length coverage, our size coverage, our burst coverage, our lock coverage, our cache coverage, everything, right? And then a million bits of cross coverage as well. So this is very, very comprehensive, and it very precisely aligns, of course, with the test plan that we had. So Chip Agents is doing a fantastic job at executing all of this. So it's done here. It's put together our transaction coverage. It put together our protocol coverage here as well. So there's an entire new file. Together, this is multiple thousands of lines of Verilog, system Verilog and UVM that's put together for it. It's wrapped this up in a nice little package file. And finally, it's actually putting together a README so that in the future, somebody else can actually read all of this and understand it quickly at a glance. There's a huge amount of customizability that you can do with chip agents. For example, you can impart not just the test plan onto chip agents, but the entire verification test bench architecture. How you set up all of the different agents, how you set up all of the different environments and all the drivers, provide that high-level block diagram and so forth to chip agents, and then it can execute on that high-level vision and architecture. DV, it is an art form, and that art is going to persist. That's really what humans are going to be providing long-term, is actually the artistry there, the wisdom from past experience, being able to impart that architectural ideal onto chip agents and have chip agents do the execution. That's really where we see the highest value. That's where you start to feel a serious force multiplier in your organization. A team of 10 people is going to start feeling like 50. As the tech gets better, a team of 10 is going to feel more like 100 and 150. Okay, so chip agents is all done here. It's put together a nice summary for me of all the different randomized sequences, the different coverage modules, and a bunch of key features for me. I can even pull up the README here, where it shows me the entire infrastructure, all of the actual files and where they live, and then all of the quick little bits of documentation here, and even a bit about basic usage and integration. If I asked chip agents to, it would set up a bunch of make files for me, or it could use a bunch of like Bazel scripts, or maybe you have a bunch of shell scripts and Perl scripts that are smashed together in order to produce your whole verification apparatus. Chip agents can integrate into that, figure out how to run all of that, and then get all this compiled, simulating, and running, so that you can start actually providing stimulus to your designer test and collecting coverage immediately. So I think that's a great introduction to the capabilities of chip agents. But one final thing that I would like to emphasize here, while this is a quick demo, we support dramatically more different features. We have chip agents being extensively used on the design side. You might take a whole core that you have, a whole SoC, and say, I need to extend this. I have a microarchitecture that's been written up. I'm going to use this microarchitecture. I want to impart that onto the design for this new feature. Chip agents will read exhaustively all of the different material in your existing core. And you might ask how many files, how many lines of code. We're talking millions of lines of code, tens of thousands of files. These are the common situations where chip agents is being used in production today. It will read all of those different files and figure out where it needs to make surgical and precise changes to your actual code to include these new different features or tune things or integrate different components. So that's on the design side. It can produce plenty of smoke tests for you. It can actually produce the modules for you. On the architecture side, architects are very interested in exploring the entire Pareto frontier of different possible microarchitectures, right? We might be wanting to integrate, let's say, some sort of DDR5 controller or some sort of similar sort of controller, and we're interested in different options, how they compare in terms of their complexity, how they compare in terms of the area, the power, and the underlying performance, right? And we want to find that Pareto frontier. Well, if your architect can dispatch the actual execution of, let's say, quick little modules that need to be utilized and tested and experimented with, your architect can work dramatically faster. They can go through 5 or 6 or 10 or 15 different options and analyze them all with respect to the PPA constraints that they're working under. Likewise, formal property verification, we have plenty of great case studies with our customers on mining invariants from either specifications directly from the English and transforming that into a set of invariants and then applying that onto your designs or test bench infrastructure, or even mining invariants from the RTL. Sometimes that can be done, and it depends, and it's up to the discretion of the FPV engineer involved. So really, at every level, we support all of these different flows. So I think that's what we'll stop here and we'll showcase just that for chip agents. We have a lot more that we can talk about. Our booth is on the first floor. You can't miss it. It's right in front. Plenty of additional work that we've done there on interesting things like root cause analysis, more design work, more test bench work, more formal property verification work. Finally, I think that if you do want to get in touch with us, again, our booth is on the first floor there. You can also go to chipagents.ai, and over there you'll be able to book a demo with us. We'll be happy to showcase chip agents to your entire team, talk about everywhere where it fits with you guys. We do specialized onboarding procedures. We work with all sorts of large companies in order to deploy them in enterprise settings, people doing SoC verification, working on data center chips, working on AI accelerators. We've worked with everybody in this space. Thank you all.
For the excellent presentation. I'm just trying to understand. You presented this bar chart where it mentioned like about 62% accuracy. So how does that translate to the demonstration you showed where, so is there like 62% accurate that what you demonstrated, or is that over multiple different designs?
Great question. So, we should differentiate, of course, between the academic work and then the productized work, right? When we build and put together benchmarks, we put together benchmarks because we come out of academia, and also we want to do good, solid work. When we improve our agents, we want to be able to track and make sure that they're doing better over time, of course. We've put together some really complicated benchmarks where we're really trying to perform debugging at very large subsystem scale, SOC scale, and that's where we're seeing the improvement, and we're able to make a lot of progress. The system that was actually demonstrated today is of extremely high quality and accuracy. When we actually work on the product side, making this technology useful and available to design verification engineers or design engineers, architects, and so forth, we actually do a lot of human evaluation. Specifically, we might take something like the AXI test plan that was produced here, we pass it off to real DV engineers who have lots of experience with the AXI protocol, and they tell us what they think of it. So we've worked side by side with all of these very experienced DV engineers, especially for things like test plans, in order to push the accuracy of our systems up very dramatically.
So you show how effective you are at keeping the agent on task to develop a sizable code base. Can you talk from your experience about dealing with a living code base and being re-entrant and keeping up to date with the fact that designs evolve through their life cycle, and how effective are agents today for bringing sequences up to date, absorbing changes to register maps, and so on?
That's a great question. Is my mic still active, by the way? Okay, great. That's a great question. I haven't heard anybody frame it as re-entrant. That's a good way to put it. All of our customers, they work with, code lives, right? It lives and it breathes, right? And you have to make sure that it's maintained and it's always up to date. So one thing that's really important to note is that the agent here that we've shown, it's far more stable across long time horizons, which is something that you pointed out in your question. Compared to a standard LLM, the accuracy kind of really falls off a cliff once you're past, 400-ish lines of code. But here we're actually generating thousands of lines of system Verilog, and it's high quality and it actually compiles. We're actually able to get that to work. That's because of the sort of self-stabilization process that the agentic loop imposes upon these intelligent systems. For code that is changing, for designs that change, our commercial customers are very successful at more or less just the way the humans work, where maybe you have updates to the design spec. You can isolate those little sections there, provide those to chip agents, and just tell chip agents, where do I need to make changes from this? The spec has changed. Where do I need to impart changes onto the rest of the code base? Chip agents is able to go through and read huge sections of your code base very, very rapidly, tell you where all of those changes need to be made, and also get you started on all of those changes. In many cases, chip agents can take the whole process from start to finish, though of course it depends on the size of the change.
So one question on when you deploy, right, what kind of infrastructure are you running your tools on, right? You showed 5 minutes you can do this, right? So on the back end, where is your compute farm, for example, right? And if your customer, should they be having their own compute farm, or do you have your own compute farm that you run on the back end? Can you give us some idea about that?
That's a great question. So when we specifically talk about compute, what you've seen here today is just not possible unless you're really using the very largest state-of-the-art models. We use only the state-of-the-art frontier models, and we use it on the state-of-the-art infrastructure. The majority of this, it's running on, we have some elastic cluster of H200s basically, and a good sizable number of them in order to actually make our technology available to all of our different customers. That runs for us, we mostly use AWS, and lots of our customers, they use AWS, and so they're comfortable with it. But there's a gradient of different options, of course. Many people, they're comfortable with our software as a service solution. There are many public companies, for example, who use our software as a service solution. Some people, they prefer single tenants. Some people we work with to do custom, more bespoke deployments. It is a complex question as to, does every single company need their own server farm? I would like to think no. We've had cloud infrastructure for a while, and more companies are starting to adopt cloud infrastructure. We think that especially because the pace of growth, just a year ago, the best thing out there were H100s, and a year before that, A100s, but actually H200s, they're dramatically faster in an end-to-end latency now. If you have to sort of set up your own server farm, it's going to be obsolete pretty soon. Cloud gives you a lot of flexibility and advantages. We are starting to see this movement with lots of customers that we actually interface with, where they're starting to be more available and, let's say, slightly more amicable towards cloud offerings precisely for this reason.
Thank you first, big congratulations for you, for arriving so good result on Verilog eval. Also thank you for mentioning our work. Actually, we are the author of the major paper, from the HSSD. And my question is, we are kind of interested in how would we build a better, more powerful tool like this in the future? Where do you think the chance will lie? Is it in the training or fine-tuning or more agentic works?
That's a great question. There's really improvements at every single level. I mean, there's even improvements at the product level. How do we actually make flows which are useful for human engineers? One thing that I like to talk about, and this is something which nobody is working on, even in research and not at the company level either, is the idea of proof. When I say proof, I don't really mean the academic type, the sort of formal type where you can get an actual 3-sat verification that something is or isn't satisfiable. I mean to say that when agents are starting to take on much larger scale tasks, they're producing thousands, tens of thousands of lines of code. Somebody else has to review that. But if you have to read thousands and tens of thousands of lines of code, that starts to become the bottleneck in whether or not you can get that code actually put into your, for example, SOC or into your test bench. So how can we actually set up agents in a useful way where they provide sort of a trail of breadcrumbs, which a experienced engineer can look at and effectively just look at a subset of the total work that's been done to have strong confidence that the overall system actually works. So this sort of light, informal, pseudo-proof, this is a sort of aspect which nobody is really working on inside of research and academia, and I think would be a fantastic fit. Because really, as agents start to get better, we really have to think about how do we even make the review process simpler for human beings who are actually doing the review.
Right. I'm curious, what foundation model is this built upon and why?
That's a great question. So, in practice, to be honest, especially when we do bespoke deployments with customers, the foundation model has to be sorted out by coming to a consensus agreement with whatever the customer is interested in doing and whatever we have results, and we of course have the set of results across a wide variety of foundation models. I can also tell you something to the tune of the foundation model we use today is a different foundation model than the one we used last month, because that's roughly the pace at which these foundation models come out. I'm not at the liberty to say this particular one. In fact, I wouldn't even know because we have an elastic infrastructure. But you can effectively think that we use the largest thing that we have. We do a lot of post-training on those systems in order to make them better at the tasks that we're interested in, and those are the systems that we deploy to customers.
Do you see yourself using an open source foundation model in the future?
Absolutely. We work closely with the open source space, and we're very interested in open source models and open source tooling as well. And of course, you get more control and more freedom. So we work with open source models, sometimes we work with proprietary models, we do all sorts of different things. Ultimately, what's important to us is that, one, we have the ability to perform some post-training on it so that we can improve that system Verilog performance and therefore make that more useful to our customers. And then two, is really just correctness at the end of the day. Correctness for us is paramount. Correctness is key to usability for our customers.
Thank you. You guys are great.
Thank you.
Thank you for the wonderful talk, and I think it seems that the demonstration today most like front-end design. I wonder if you have done anything in the back-end, like placement and routing, like this sort of functionality.
Great question. That's a very important point. At the current moment, we are more focused on the front end, I like to say basically up to and including synthesis, but it's also a very interesting problem, Agents have shown preliminary good results on doing things like writing CUDA kernels, for example. They can write very solid CUDA kernels, which are now performing on par with, in some cases, what human experts are actually able to produce for individual kernels that are dispatched on GPUs, right? In the same way, we're actually interested in having agentic processes that go through and they actually write the different constraints that you're using in order to do synthesis in order to achieve better PPA metrics, right? So that's a similar task that we are interested in doing and interested in working on. We are in fact always looking for people who have experience with these particular niches. Anybody who works at the intersection of really AI and EDA, especially on both the front end, on the back end. These are all projects where we have our fingers in all these different pies. So anybody who is interested and has this sort of experience, you can swing by our booth, and we have lots of different offerings and openings for different people working on this.
Thank you.
question on scale. First of all, this is amazing on the AXI spec. I've actually done the AXI spec myself, and yeah, this would have been nice. Where is the scale going, and how far are you away from, let's say, taking a subsystem where you have a couple of processors, a more complex protocol like a CMN, some peripherals? Where do you see, or how and when do you see yourself approaching that scale? And then in the context of what you showed, going from spec to RTL, is there like a way to articulate how you connect those components? I mean, I would use IPexact as a developer to plug them together, but would you just show them a block diagram and feed that in, or how would you do that?
That's a great question. The subsystem level is actually attainable today. I'd say smaller subsystems when you're looking at, like, I don't know, 3 to 5 components or so forth. That's actually a very common use case today. And I'd say that's where people need the most help as well, because you're starting to get into additional, more complex systems. There's more protocols, more specs that are interacting with each other, and it starts to become kind of like at the edge of what you can fit inside of your head. For specifically providing information to chip agents, the block diagram works great. We do support, image, multimodal input. You can provide block diagramming languages. I sometimes am partial to Mermaid.js. For example, many of our customers use that. You can provide that information to chip agents in order to specify the high-level architecture details. One great thing about hardware design is that it's very hierarchical. Because it's so hierarchical, I mean, we're literally working with blocks. This is actually quite amenable to agentic AI, because this means that we can put together blocks with code. When the scale of the design increases exponentially, you actually see some sort of sub-exponential, probably linear, increase in the actual amount of code being written, which is how we're able to actually scale up to that level. Thank you so much.